Last time we left off, we were looking at concentration of solutions. We're not going to do any math, we just want to be familiar with different units for concentration. Like for example, percent or parts per 100 parts, which is a solute percentage. Or milligrams per deciliter, which is good for glucose measurement and cholesterol counts. Or molarity, which is quite common, which uses a capital M as its unit. And we're going to look at one example of how to get molecular weight, because 1 mole, or what is it, the atomic weight of an element, is the same thing as molecular weight. So to calculate molecular weight for a compound, we would want to take the masses of those compounds from the periodic table, make sure that we represent how many of that particular element or atom is in the compound, and then add the weights together. So for example, if you have water, you have 2 hydrogens and 1 oxygen atom. The atomic weight or mass of hydrogen on the periodic table is 1.01. That's slightly rounded. And there's 2 of them, so times 2, that's 2.02. For oxygen, it's 16 on the periodic table. And we only have 1, so times 1, that's still 16. And if we add 16 and 2.02 together, we get 18.02 grams per mole, or the molecular weight of water. Our next topic is going to be chemical bonds, and chemical bonds are an energy relationship that hold atoms together. When we're talking about chemical bonds, we're going to be talking about electrons, and electrons particularly in the outermost energy level or valence shell, which is also known as the valence orbital of atoms. So electrons can occupy up to 7 electron shells, which we can think of as energy levels around the nucleus, and the ones that are in the outermost shell are going to be the ones that are reactive with other atoms. So they're the ones in the valence shell that are going to be involved in chemical bonds. So we have an octet rule, or the rule of 8s, that gives us some more information about how these electrons in the valence shell are going to behave. What the octet rule says is that atoms that are reactive want 8 electrons in their valence shell, that they desire these 8 electrons in their outermost energy level, and that's the driving force behind chemical reactions. An example of atoms that are completely happy are the noble gases, because all of them already have full 8 electrons in their valence shell. There is an exception. If an atom only has 1 orbital because it doesn't have a lot of electrons, it's happy with 2 electrons in its first orbital. But for the rest of the orbitals that are outside that first orbital, we want 8 electrons. If you wanted to see the noble gases, they are in column 18 on the periodic table, and they're rare compared to most atoms because most atoms don't have full valence shells. Therefore, atoms either want to gain, lose, or even share electrons in order to form bonds and become happy or stable atoms. So if we look at this periodic table, you go all the way over here to column 18. These in dark green, they are the noble gases, and they have 8 electrons in their valence shell. So we would call those types of atoms inert or non-reactive atoms. They're not interested in forming bonds with other atoms. So here are also 2 chemically inert or non-reactive elements. So we can see helium, which is really small. It only has 1 orbital for its 2 electrons. And for the first orbital, 2 electrons is fine. That's the exception to the wants 8 rule for the octet rule. Over here, neon slightly larger, and it has 10 electrons. So 2 in the first one satisfies the octet rule, and then 8 in the second one satisfies the octet rule. Both of these atoms are completely stable and happy. They don't want to form any bonds with any other atoms, so they're inert. But most atoms are actually chemically reactive. They want to gain, lose, or share electrons. For example, hydrogen would like an extra electron, so it had 2 in the first valence shell. Carbon would like 4 more electrons. And oxygen over here would like 2 more. Or oxygen could get rid of these 6 electrons, but that might be difficult. Whereas sodium would either need 7 more in the outermost shell, or it would need to get rid of this 1 extra electron, which is actually going to be the easier thing to do for sodium. It's a lot easier to get rid of 1 electron, and then the outermost shell would be the one under that with 8, and it would be happy, than it would be to gain 7. So again, our chemically reactive elements are either going to gain or lose electrons, or share electrons. So that brings us to our types of chemical bonds. Again, the electrons are what are involved in the chemical bonding, but our types are ionic bonds, covalent bonds, and hydrogen bonds. Now, when we consider bonding behavior, the only thing we're looking at are the electrons, and not just the electrons, we're looking only at the electrons in the outermost energy level, or the valence shell. These are the ones involved in chemical reactions. And if we're looking at an inert atom that's full to 8 in its outermost shell, or if it has one orbital 2, then it's not going to react with other atoms. So again, keep in mind the octet rule, and now we're going to apply the definitions of ionic and covalent bonds to how these atoms behave. So first and foremost, when we form ionic bonds, we see a transfer of electrons. One atom is going to give up electrons, and the other atom is going to gain electrons. If most atoms are neutral, if they were to lose an electron, they would suddenly have more positive than negative charges, and that particular atom would become a cation, or an ion with a positive charge. The ion that gains an extra negative charge, if it started out neutral, has now gained more negative charges compared to its positive charges and has an overall negative charge. The ion that is negative is called the anion. I just think of ants as something negative. I don't want to deal with them. I definitely don't want to be bit by ants. And then if someone were to hand me a cat or a kitten, that would be a positive experience. So that's how I remember that anions are the negative ion and cations are the positive ion. With ionic bonds, we're not just seeing the transfer, we're seeing the loss or gain of electrons by those atoms that are participating in the ionic bond. And when you dissolve the substance that's forming an ionic bond in water, you'll see the individual ions, and their charges will remain on the separate ions. So let's look at an example of ionic bond formation. Here we have sodium and chlorine on the left, and then sodium and chloride ions on the right. So the ones on the right have satisfied the octet rule and are now happy but have charges. So they have formed ionic bond. They would only dissociate or separate from each other if dissolved in water. Because when sodium and chloride are together in an ionic bond and they're dry, they're not dissolved in water, they actually form table salt. But let's start at the beginning. We have sodium, which had that one lone electron in its outermost valence shell. And then over here, we have chlorine, which has 7 electrons in its outermost shell. Well, both of these atoms could be completely stable, happy, and inert if sodium transferred its electron to chlorine. And that's exactly what happens. Once that occurs, we are going to use this orbital, which was below the original outermost shell, as the outermost shell for sodium. And we got rid of an electron, so now sodium's positive. This is the cation. And then for chlorine, it's now chloride with a negative charge because it got an extra electron. That extra negative charge now gave chloride 8 electrons in its outermost valence shell. And most ionic compounds are going to be salts. And we just talked about when they're dry, they form crystalline structures. And crystalline structures like sodium chloride, which is table salt, are commonly formed when you desiccate or dry out an ionic bond. So here is an example of crystals instead of individual molecules, because this is a demonstration of ionic bonds that are in a dry environment instead of being dissolved in water. Most of the time we study the ions created of an ionic bond once we've dissolved it in water. They're just easier to study separately. Next, we're going to look at covalent bonds, and if ionic bonds transfer, if that's the key word there for ionic bonds, covalent bonds share electrons. So ionic bonds transfer electrons, covalent bonds share. We can share 2 electrons, which is 1 pair of electrons to create a single bond. We can share 4 electrons, which is 2 pairs of electrons to create a double bond. Or we can share 6 electrons, which is 3 pairs of electrons to create a triple bond. And the reason, again, that we're sharing electrons is to fill the outermost valence shell and to make sure that these atoms are happy and that they're meeting the octet rule. There's two types of covalent bonds. We have polar and nonpolar covalent bonds, and this has to do with whether or not we're going to be sharing the electrons equally or unequally. For example, here we have 4 hydrogens and 1 carbon on the left, and the 4 hydrogens only have 1 electron in their outermost energy level or valence shell. They would like 2, because remember that innermost or that first orbital is happy with 2. Whereas carbon has 2 orbitals and its outermost would like 8 and it only has 4. So we can make all of these atoms happy if carbon forms 4 single bonds with the 4 hydrogen atoms. And the rule for covalent bonds is if you're sharing electrons, you get to count both electrons for each atom. So this pair counts for hydrogen, and both of these would count for carbon. So this hydrogen has 2 on its first orbital, which is fine. 2 on this hydrogen, 2 on this hydrogen, 2 on this hydrogen. And the first orbital around the nucleus, remember, is happy with 2. It's only the second and furthermore that would like 8 in order to satisfy the octet rule. For carbon, we also get to count all of the pairs. So if we were looking at the outermost shell of carbon, once it's formed 4 single bonded covalent bonds, we would say that the outermost shell has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that means that carbon is happy, it's stable. By forming those covalent bonds, all of the atoms have satisfied the octet rule. Here, if these oxygen atoms share these 4 electrons, they form a double bond because it's 2 pairs. And we get to count all 4 of these electrons for both oxygen atoms. So we are going to go from having 1, 2, 3, 4, 5, 6 originally, like these over to the left, to now being able to count these last 2, 7, 8, for both oxygen atoms. So we count 1, 2, 3, 4, 5, 6, 7, 8. So you count all the shared electrons for both atoms. And here's a triple bond, so we have 6 electrons, 3 pairs. This is how you'd write a triple bond in a structural formula. And we could count all of the shared electrons for both nitrogens. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, and it'd be the same for the other nitrogen atom. Whereas originally both nitrogen atoms only had 5. So only 5 in the outermost shell, so they wanted more in order to be satisfied. Now, if we share electrons equally, we would form a nonpolar molecule. Equal sharing means not one side is going to be slightly negative and the other side is going to be slightly positive because the electrons are closer to one atom than the other. That doesn't happen with equal sharing of electrons, so that would form a nonpolar covalent molecule. Unequal sharing of electrons does create that slightly negative side and that slightly positive side to a molecule. It creates a polar molecule because we consider the side that's slightly negative versus the side that's slightly positive two separate poles. So that's why it's being called a polar molecule. Like North and South Pole, we have negative and positive pole. We're going to look at 2 examples. We're going to look at CO2 and H2O, or carbon dioxide and water, for our examples of equal sharing of electrons and unequal sharing of electrons, respectively. Alright, if you want to see this video, just send me a message and I'll send you the parts of an atom video link. It should still be working, so again, just email me or text me if you want that link. Alright, here we have equal sharing of electrons. We're looking at carbon dioxide, which forms a double bond with 2 oxygen to a carbon. So here's carbon, here's 2 oxygens, they're double bonded together. All of these atoms are about the same size. And so since they're all about the same size, there's not going to be one atom that's pulling the electrons closer to itself than the other. And so there's no pole, there's no slightly positive or slightly negative pole. We would say in general that the electrons tend to be right between these atoms. So this is a non-polar demonstration of equal sharing of electrons. Whereas with unequal sharing of electrons, you're going to have one of the molecules be slightly more electronegative or just really a lot larger than the other molecules. Here we have water and we have the oxygen molecule, which is much bigger than the two hydrogens. And so kind of like a planet has a gravitational force, we can think of oxygen as a planet, and it's a much bigger planet than the hydrogen planets, and it's going to pull the electrons a little bit closer to itself. The ones that are being shared with the hydrogens, it's going to pull them a little bit closer to itself, so the oxygen side is going to become slightly negative. So that's slightly electronegative, whereas since the electrons are closer to oxygen, the hydrogens don't have those electrons as close to them. Those sides are going to become slightly positive. And so that creates two poles, a negative and a positive pole. And that's why we would consider this example to have a dipole and demonstrate unequal sharing of electrons and therefore form a polar molecule. It forms poles in the molecule, therefore it's polar. So all those atoms that we were looking at have different electron attracting abilities, and if it leads to the unequal sharing that we saw with water and the formation of a polar covalent bond, then those two poles we would call electronegative or electropositive. This is commonly seen and demonstrated with water. So H2O is definitely a polar molecule. It's always a polar molecule because oxygen is more electronegative. So again, it's exerting a greater pull on the shared electrons. They're closer to oxygen. That gives the oxygen a partial negative charge, whereas since the electrons aren't as close to the hydrogens, they're going to have a partial positive charge. And again, the name for that was a dipole, which is created in a polar molecule. Here's a good quick guide for looking at ionic, polar covalent, and nonpolar covalent bonds compared to each other. Remember, ionic bonds transfer electrons to form an anion and a cation. Covalent bonds, we're going to see sharing of electrons, either unequally to form a polar covalent bond or equally to form a nonpolar covalent bond. So take some time, look over this chart. Please let me know if you have any questions. And then next we're going to look at hydrogen bonds. Hydrogen bonds are weak, they're more of an attraction, but if you have a lot of them, they're really strong. We use hydrogen bonds to hold the two strands of our DNA together. But a hydrogen bond by itself is not as strong as an ionic or a covalent bond. They're just an attractive force between those electropositive and electronegative parts of molecules. So these are going to be between molecules, not between atoms. So essentially these are intramolecular bonds, not intermolecular bonds. And they're what is basically responsible for surface tension in water and some of the other characteristics of water that we'll look at next week. So here are our intramolecular bonds. Covalent bonds would be between, for example, hydrogen and oxygen, but the intramolecular bond here is a hydrogen bond and it's depicted with this dotted line. What you're seeing is the electronegative side of oxygen attracted to the electropositive side of hydrogen, which is making up the water molecules. And that's happening throughout this image. For example, we have positive to negative, and so we're forming these weak attractions between water molecules. And here's an example of the surface tension created because of the intramolecular hydrogen bonds. Small insects like the water strider are able to walk on pond water because of the high surface tension of this type of bond, especially created in polar molecules like water. Alright, next we're going to be looking at chemical reactions, so make sure you watch that video, and then we'll finish up part A for this week.